Hi, today I will show you how to configure the UART in the TIVA board in order to print messages to a serial console. The core of this board is an ARM Cortex-M4F with a maximum frequency of 80 MHz. It also contains a pretty cool RGB LED to play with it. It has 2 user switches and has 4 main clock sources. Today, we will use the Precision internal oscillator with a frequency of 16 MHz. And also, this board includes 8 fully programmable UARTs. I'm going to show you the code so that if you don't want to go through my long explanation of how everything works, you can just copy the code and analyze it by yourself. That is the purpose that I'm showing you this code from the beginning of the video. I'm going to compile it and okay, I'm just going to show you how it works. You need to create a serial console. The way that you can do it in Code Composer is just like this. You need to create a new one and just name it like you want. Okay, 9600 baud rate, and I think that's everything. And I'm just gonna press the play button, and as you can see, it is sending the message 200. That is the data that I'm sending, just to show you that it works. And I think that that's pretty much everything that you need to start with this code. Okay, the PA0 and PA1 pins can provide connection to a serial console through a virtual COM port. PA0 is the receiver pin and PA1 is the transmitter pin of the UART0 peripheral. The RCGCUART register provides software the capability to enable and disable the UART modules in run mode, so here you need to enable the clock of UART0. The PRUART register indicates whether the UART modules are ready to be accessed by software following a change in status of power, run mode clocking, or reset. Here, you need to execute a while loop to wait until the UART module 0 is ready for access. The RCGCGPIO register provides software the capability to enable and disable GPIO modules in run mode. When enabled, a module is provided a clock and entries to module register are allowed. Here, you need to enable and provide a clock to the GPIO port A in run mode. The PRGPIO register indicates whether the GPIO modules are ready to be accessed by software following a change in status of power, run mode clocking, or reset. You need to implement again a while loop in order to wait for the GPIO port A activation. The UARTCTL register is the control register. All the bits are clear on reset except for the transmit enable and receive enable bits, which are set. To enable the UART module, the UART EN bit must be set. If software requires a configuration change in the module, the UART EN must be cleared before the configuration changes are written. First, you need to clear the bit 0 to disable the UART. The GPIOAFSEL register is the mode control select register. If a bit is clear, the pin is used as a GPIO and is controlled by the GPIO register. Setting a bit in this register configures the corresponding GPIO line to be controlled by an associated peripheral. So, this is why you need to enable the bit 1 and 0 as they are associated to the PA1 and PA0 pins. The GPIOPUR register is the pull-up control register. When a bit is set, a weak pull-up resistor on the corresponding GPIO signal is enabled. In this register, we need to clear bit 1 and bit 0 to disable the pull-up resistor. In the GPIO PDR register, when a bit is set, a weak pull-down resistor on the corresponding GPIO signal is enabled. This is the same case as the previous register. We need to clear the first 2 bits in order to disable the pull-down resistor. This register is the data direction register. Setting a bit in this register configures the corresponding pin to be an output, while clearing a bit configures the corresponding pin to be an input. Since PA0 is the receiver pin, you need to set it as an input. Therefore, PA1 must be configured as an output. The GPIOPCTL register is used in conjunction with the GPIOAFSEL register and selects the specific peripheral signal for each GPIO pin when using the alternate function mode. Here, you need to verify the digital function value in the GPIO pins and alternate functions table within the datasheet. As you can see in the table of this slide, you need to write a 1 into the PMC0 and PMC1 bits. In the digital enable register, you just need to indicate that the digital function for the PA0 and PA1 pins are enabled. This register is the integer part of the baud rate divisor value. To calculate this value, you just need to use the formula from the top of the slide. For me, the clock frequency is 16 MHz, the clock divisor is 16, and the baud rate is 9600. Therefore, 104 is the value that I need to write into this register. Now, this register is the fractional part of the baud rate divisor value. Here, you just need to multiply by 64 the fractional part of the previous division. The UART LCRH register is the line control register. Serial parameters such as data length, parity, and stop bit selection are implemented in this register. In the WLN register, indicate that 8 is the number of data bits that will be received or transmitted in a frame. And also indicate that FIFO buffers are enabled. You have to write a 0 in the high-speed enabled bit to indicate that the UART is clocked using the system clock divided by 16. Also, enable the receive and transmit sections, and now you can indicate that the UART is enabled. In this case, this while loop will be executed until UART0 FRR is different from 0, which means that the FIFO is full. This register is the data register. It contains the data that will be sent. Data written to this location is pushed onto the transmit FIFO. Okay, you will need to add a for loop after the UART configuration. And as you can see, the value 1667 indicates how many clock cycles takes the duration of a bit. One iteration of the for loop takes approximately 3 to 4 clock cycles, so if we divide this value by 4, we guarantee that the UART has enough time to be configured and that is ready to send a message. I think that this is everything that you need to know to successfully understand how the UART0 peripheral is configured.